Welcome back to AI.Code.Cast, ready for another deep dive.
Absolutely. Always up for a challenge.
This one's got our community buzzing. It's all about maximizing that minimum magnetic force between balls placed in baskets.
Okay. I'm intrigued. Lay it on me.
So picture this. You've got EM baskets just kind of scattered around, and the magnetic balls. But these balls, they repel each other.
Repelling balls. All right. Got it. So what's the goal here?
We got to arrange those balls in the baskets so that even the two that are closest, they're pushing each other away like it's their job.
So we're not just going for total magnetic chaos. It's more about like a strategic, balance of forces.
Exactly.
Yeah.
And that's what makes this problem, tricky. There's not some obvious solution right off the bat.
Yeah, I can see that.
So before we get all fancy with algorithms, what if we just went full caveman? Brute force. Just try every combo of ball placements and see what gives the strongest minimum push.
Well, I mean, in theory, you could totally do that. Systematically plunk those balls down, calculate all the forces between every single pair, and then just keep track of, the weakest link in each setup.
Right, the one with the biggest minimum force. That's our winner.
Exactly.
Seems easy enough, right?
Yeah.
But is that really going to fly, especially if we have a ton of baskets and balls?
That's the catch with brute force. It gets out of hand fast. Like imagine 10 baskets and 5 balls.
10 baskets, 5 balls. Not that many, really.
Right. But even then, the number of combos explodes. It's like trying to find a specific grain of sand on a beach.
Okay, yeah. Brute force is out then, at least for anything beyond a tiny setup.
Right.
We need something smarter. But hold on, before we get to that, there's this question that keeps popping up. Does it actually matter how strong the magnets are themselves?
That's a sharp observation. And it really points to the core of what we're after here. It's less about the raw magnetic power and more about the relative distances between the balls. Think about it. Whether the magnets are super strong or kind of weak, our goal is the same. We want to max out that minimum distance between any two.
So it's a spacing game.
Spacing is king.
Okay, so that simplifies things a bit. No need to get lost in complex force calculations. But what about pitfalls? Are there any common traps people fall into when they're first tackling this?
Oh, absolutely. A big one is getting sucked into what we call local optimization.
Local optimization, okay.
You might think, all right, I'm going to space out these first few balls way far apart. Brilliant. But then you end up kind of painting yourself into a corner, and suddenly you can't fit the rest of the balls without ending up with some that are way too close.
It's like a magnetic Tetris, where if you're too greedy at the start, you end up with a lousy score.
Perfect analogy.
So you got to plan ahead, think about the big picture, not just each individual ball.
You got it. Global optimization is the name of the game.
Any hints on how we get there?
Well, what if instead of focusing on placing the balls directly, we shifted our focus to finding that ideal spacing between them?
Like setting boundaries.
Precisely. If we can figure out the biggest minimum distance that lets us fit all the balls in, we've got our blueprint.
Ooh, it's like finding the perfect grid size for our magnetic Tetris. But how do we find that magical distance?
That, my friend, is where binary search comes in. No more random guessing. We're going systematic. Narrow down the possibilities until we pinpoint the largest distance that actually works. Binary search, it's kind of like having a superpower, right? You can find things crazy fast.
Okay, I'm all for superpowers. But how does it work for this problem? It's not like we're searching a list for a number. We need the perfect spacing for these feisty balls.
Think of it like this. All the possible distances between the balls, they're on a ruler. Yeah.
Mm-hmm.
Binary search is going to start smack dab in the middle of that ruler, checking that distance first.
So it's our first guess, right? But then we got to see if it actually works, if we can space those balls out that far and still make it happen.
Right. And for that, we'll need a way to test it. A little helper function within our main algorithm.
So it's like a mini algorithm inside the big one.
Exactly. And let's call it, how about can place balls?
Can place balls. I like it.
So this function, it takes that distance we got from our binary search and tries to arrange the balls, keeping them at least that far apart.
Okay, so it's like we start with ball number 1, plop it in a basket, and then we got to find the next basket that's far enough away to put ball number 2, and so on.
You got it. Kind of like a greedy algorithm, always grabbing the first spot that meets our distance rule.
But what if it gets stuck? What if there's no basket far enough away for the next ball?
That's where things get interesting. It could be that the distance we're trying, it's just too big. We got to go back to our binary search and try a smaller one.
Right, scale it back a bit. But I'm also thinking, what if we just got unlucky with the order we tried placing the balls? Maybe there's another way to arrange them that would work with that same distance.
You're totally on the right track. Just because our first greedy attempt failed doesn't mean the distance itself is a no-go. Maybe we need to be a bit more strategic about our placement.
So we need can place balls to have some options, some way to try different things if it hits a wall.
Exactly. Some kind of backtracking mechanism. If we run into a dead end, we can back up, reconsider some of our earlier choices. Maybe placing a ball in a different basket earlier on opens up possibilities down the line.
Ah, so we're exploring different paths, seeing if any of them lead to a win.
Yeah.
But doesn't backtracking risk making can place balls really slow? We don't want to lose all the speed we gained from using binary search in the first place.
Great point. We got to strike that balance, exploring different arrangements, but not getting bogged down in trying every single permutation under the sun.
So we got to be smart about our backtracking. Prioritize certain paths, maybe, or recognize patterns that tell us, hey, this way is going nowhere fast.
Now you're thinking like an algorithm designer. We can use heuristics, optimizations, make that backtracking process more intelligent.
So it's like, can place balls is learning as it goes, getting better at navigating all the possible arrangements. It's like a little AI inside our main AI.
Love that. And it shows that even in a seemingly simple function like can place balls, there's tons of room for creativity and optimization.
Man, this is getting deep. We've gone from brute force to binary search with a greedy helper that also does backtracking. Like a multi-layered solution, each layer adding more power.
And all working together to crack this tough nut. So we've got can place balls. We see how it uses backtracking to explore different options. Now let's zoom back out and see how it all fits within our binary search strategy.
Right, so we've got this can place balls function. It's like our little detective snooping around, figuring out if a certain distance will actually work for all the balls.
And not just checking, right? It's trying different arrangements, using that backtracking we talked about.
It's not giving up easily. But let's zoom out a bit. How does can place balls work with binary search to actually nail down that optimal solution? You know, the biggest possible minimum distance.
Okay, picture this. Our range of possible distances, it's like a line, right? Binary search is going to start by picking the middle of that line. That's the first distance we give to can place balls.
So it's our first guess. Then can place balls goes and tries to place all those balls, keeping them at least that distance apart. What happens next?
Well, there's two things that could happen. Let's say can place balls comes back and says, yep, we're good. All balls placed, no problem. What does that tell us?
Well, maybe we've found the best distance. But maybe we could space them out even more and still make it work. So we need to look at the bigger distances, right?
Bingo. Binary search is all about efficiency. If that middle distance works, any smaller distance is definitely going to work too. We can just chuck out that whole lower half of our range just like that.
Okay, yeah, that makes sense. But what if can place balls comes back and says, nope, no can do, can't fit all the balls with this spacing?
Well, then we know our middle distance was too optimistic. The best solution has got to be somewhere in those smaller distances. Again, we get to eliminate a whole chunk of possibilities with just one check.
So we keep cutting the range in half, using can place balls to tell us which way to go until
We've narrowed it down so much that our range is basically just a single point. At that point, we found the biggest possible minimum distance that lets us place all those balls.
It's amazing how fast binary search homes in on the answer. Like instead of searching every inch of a room, you just keep splitting it in half till you find what you're looking for.
Exactly. That's why it's so much faster than brute force, especially when things get complicated with lots of baskets and balls.
Well, this has been one heck of a deep dive. We started with a pretty simple idea and ended up with a really sophisticated solution using binary search, a greedy helper function, and even a bit of backtracking.
And it's not just about this one problem, right? These techniques are like tools you can use for all sorts of challenges where you need to find the best value within a certain range.
Exactly. Binary search, it's like a superpower for programmers. So next time you're trying to optimize something, think about whether you can turn it into a search problem and let binary search do its magic.
Thanks for joining us on AI.Code.Cast, everyone.
And keep those challenging problems coming. We'll be back to break them down with you.